Welcome back to the third talk of the afternoon session. This is still FPSAC 2021. And we have Matias von Bell on frame triangulations of flow polytopes, the new Tamari lattice and Young's lattice. Please.
Thank you very much. And thank you to the organizers, and thank you for everyone for being here. I'm pleased and honored to be here with you to talk to you today about frame triangulations of flow polytopes and new Tamari lattices and Young's lattice. And I want to stress that this is joint work with Rafael Gonzalez de Leon, Francisco Mayorga Cetina, and my advisor, Martha Yip. So to get started today, I think it'd be a good idea to define what this new is. So a lot of the talk is based on this new, and that is a lattice path from the origin to some point A, B in the first quadrant using your standard steps, north and east steps. And once we fix the path new, then we can define new-dic paths to be lattice paths that stay weakly above the path new. So for example, on the right here, we have a new-dic path. It stays weakly above the gray shaded region. And standard terminology for new-dic paths is the valley is a consecutive east-north pair. So here we have an east-north pair that are consecutive, so that forms a valley. And we have two peaks, 1, 2. And the reason for calling those valleys and peaks are, of course, obvious when you tilt your head 45 degrees to the left and see that it looks like a mountain range. And new Catalan numbers can then be defined to be the number of new-dic paths. New Catalan and new Narayana numbers as well can just be the number of new-dic paths with exactly k valleys. And so this is a nice generalization of the classical cases, where the classical cases can be recovered if we pick our path new to be the staircase path. And by the way, if there are any questions in the chat, I won't be able to see them, so please let me know. So a very well-known lattice structure on these new-dic paths comes from Young's lattice, which is, of course, the lattice of integer partitions ordered by inclusion of Young diagrams. And so here's a Hasse diagram of a portion of it. And we'll be looking at principal order ideals today. So if we pick some sort of particular partition here or Young diagram, then we look at the downset or the principal order ideal generated by it. And that gives us a lattice. And it gives a lattice immediately on the set of new-dic paths. By the obvious correspondence here, you take this partition here and look at the region above the new-dic path here. And there's an immediate correspondence there. And the cover relation on this lattice on the right in the principal order ideal is, of course, that path pi1 is covered by pi2 if and only if pi2 is obtained from pi1 by replacing one of these peaks with a valley. So here I have a peak and it gets replaced with a valley, and therefore this path on the top covers the one on the bottom. And so that's one lattice structure on these new-dic paths, but another one, in order to define that, we need this notion of horizontal distance at a point P for a new-dic path. And the horizontal distance at a point P is the number of east steps that can be taken from that point P without crossing new. So a little example of that here, here's my point P. I can take 1, 2 steps. And then if I took a third step, I would cross over into the gray region that's below new. And so I can only take 2 steps, and therefore the horizontal distance at P is 2. And in this case, shifting P down 1 unit, then the horizontal distance is 0 because I can't take a single east step without crossing new. And with this notion, we can define a rotation of pi at P by switching the preceding east step, which is here, of that point P, And P here has to be on a valley point. And then you trace along the nudec path pi here to the next point at which the horizontal distance is the same as that of P. So the horizontal distance here is 0 as well. And just a note on the horizontal distance on the top, it's just the distance to the end of the rectangle, to the top right-hand corner of the rectangle. Once you identify these points P and Q, then you take the preceding E step of P and shift it to the end while shifting everything in between P and Q 1 unit to the left. So you obtain this rotated path. And so that's the operation on these nudec paths that you can do that will generate a different lattice structure. The cover relation here is that one path is covered by another if it's obtained from the other by a from one of these rotation operations. And this is the definition of the Newton-Murray lattice given by Préville, Rattel, and Viennot. And so it's the lattice of nudec paths induced by the transitive closure of this cover relation. And some nice examples here on the left. If we use the classical, in the classical case, we have obtain the classical Tamari lattice, where nu is the staircase path. And then in the running example that we've been looking at, we obtain a new Tamari lattice that looks like the one on the right here. Okay, so these are the two lattice structures that we'll talk about today, and they're going to be coming together in a particular polytope, and that's a particular flow polytope. And so I'll introduce those next. Flow polytopes were, their combinatorial study was introduced by Baldoni and Verne, and also by some unpublished work from Stanley and Posnikov. And also there's since been lots of good work on flow polytopes, very interesting stuff by Carola Meseros, our earlier speaker today, and also Alejandro Morales and others. But to define a flow polytope, you begin with a graph G, where it's a graph with vertex at n, and all the edges in the graph are ordered from smaller vertices to larger vertices. And then you can define a flow of size 1 on this kind of a graph to be a tuple associated with the edges of the graph, where the tuple is non-negative real numbers, so that flow is preserved in the graph. So what that means is the inflow in the graph, which is what this first set of equalities here that I circled, that tells us that the inflow and the outflow has to equal 1 if you think of this as a system of pipes where liquid is flowing through, for example. And then the second set of equations tells us that the inflow and outflow at a single vertex has to be the same if it's not the source or the sink. So whatever flows in has to flow out. So if the flow is 1/2 and say 1/3 at this vertex 3, then whatever flows out has to be the sum of those. So maybe 5/6 and 0, for example. Okay, so then you collect the set of all flows of size 1 into, if you think of that set as living in R to the number of edges in the graph, that ends up being a convex polytope, and that's called the flow polytope of the graph. And the vertices of the flow polytope are obtained by considering routes in your graph. So a route is a path from the source to the sink, here to here. And if we put unit flow in all of the edges in this route and 0 flows everywhere else, then you obtain a vertex in the flow polytope. So that's flow polytopes. And next we'll have to talk about some triangulation techniques or a triangulation technique for flow polytopes. And that comes from this notion of a framing on the graph. So framing is just defined on a single vertex to be a linear order on the incoming edges and the outgoing edges. So in this case, I ordered them from top to bottom, 1, 2 on the left and 1, 2, 3 on the right. And then this framing induces this coherence relation on routes, where the incoming portions of the routes have to be ordered the same way as the outgoing portions of the routes. And if that's the case, then they're said to be coherent. So here, assuming we have the same framing as we do up here, then these routes are coherent at this vertex I, because the incoming portion of P is comes before Q as it comes in, and it also comes before Q as it leaves. But if we were to flip these two around, then those are no longer coherent as down here, unless we change the framing, in which case they might be coherent with a different framing. And also another point to mention here is that if we have multiple sets of vertices that are shared between P and Q, then we go to the previous vertex before which they differ to compare them, and then go to the next vertex after which they differ to compare them there. All right, and same thing if we swap the orders here, then it's not coherent on the bottom. So this is this notion of framing induces triangulation on flow polytopes, and this is a result also by Danilov, Karzanov, and Koshevoy in 2012 that appeared also in FPSAC. And it says that the maximal sets of coherent routes in a framing of G determine simplices in the regular unimodular triangulation of the flow polytope. And so a quick, nice little example here. If this is my graph G with 5 routes, then I collect the maximal collections of coherent routes. In this case, there are 2 such collections. They only differ by this route and this route, which I'm assuming here that the framing is this framing where we draw the order of the incoming and outgoing edges from top to bottom. And so in that case, these 2 that I circled in here, they would be not coherent. So they have to go in different sets of coherent routes. And there are 2 such collections. So then the flow polytope has volume 2 with, and this induces a regular unimodular triangulation. Okay, so with all that said, we'll introduce the star of today's talk, and that's the new Caracal flow polytope. It's constructed from a path nu. That's, for example, here on the left, taking this one, by looking at the number of north steps, adding 3 and considering the path graph on the number of north steps plus 3 vertices. And here, if we then add some more edges below from all the inner vertices to the sink here, and then add some more edges based on the number of E steps in the path. So here the horizontal runs of E steps are 2, 1, 0, 3, and 1, the lengths of them. And so then we add accordingly edges to the graph G here. So 2 horizontal steps at level 1. So we add 2 edges here from 1 to 3. 1 E step at the next level. So we add 1, then there's 0. So we skip adding edges there. And then there's 3 in the next one. So we add 3 edges to the next vertex and 1 last one here. So we obtain this nice little graph, and it's called the new Caracal graph. And if you're a Spanish speaker, you might know that Caracal is the Spanish word for snail, and that these are named after snails because they look like beautiful little snail shells. And the flow polytope over these graphs is then the new Caracal flow polytope. And this was considered by our earlier speaker, Carola, and also Alejandro Morales in 2019. And they determined that its volume is given by this determinantal formula here, which not only counts the number of Newdick paths, but equivalently counts the number of subpartitions of a partition. So its volume can be computed with this formula, but we're interested in its triangulations. So we triangulated it using a couple different framings to see what happens. And first result is that if we triangulate it with the planar frame triangulation, which is, I'll tell you in a second what that is, then you obtain the dual graph of the triangulation is the Hasse diagram of the principal order ideal generated by Nu and Young's lattice. So the planar framing here order all the incoming and outgoing vertices from top to bottom according to this planar drawing of the graph. So 1, 2, 3 coming in, and then 1, 2 from top to bottom in this planar drawing. And with that framing, the dual graph is then the principal order ideal in Young's lattice generated by this Young diagram above the path Nu. So if you go to your Hasse diagram in Young's lattice and find that corresponding partition, and then the downset or principal order ideal gives you the dual graph. So that was one particular framing. And using this framing, you can compute the H star polynomial of this Nu Caracal flow polytope. And that is the Nu Narayana polynomial. And it can be, the proof outline is as follows. So first of all, this polytope is a lattice polytope. So its H star vector is the same as its H vector for any unimolecular triangulation of it. And since since frame triangulations are unimodular triangulations, then we can simply find the coefficients of the H vector of the triangulation. And then you can show that a linear extension of this lattice, that's a principal order ideal in Young's lattice, that any linear extension of it gives a Schelling order for the planar frame triangulation. And then from there, the H vector, the coefficients in the H vector can be determined from the poset by HI equaling the number of elements in the poset that cover exactly I elements. So let me compute I2 here. H2, we have 2 elements that cover exactly 2 other elements in the poset. So H2 is 2. How many cover exactly 1? There are 4 of them. So H1 is 4. And then there's 1 that doesn't cover any. So H0 is 1. And the cover relation in this poset is, of course, the peak to valley relationship. And so the number of elements a path here covers is equal to the number of valleys that it has. So that's why it's we immediately get that it's the Narayana number here. And so one thing you'll notice is that this H star vector is not symmetric. So we have 2x squared plus 4x plus 1. Okay. The other triangulation that is also of interest is obtained by a length framing of the graph. And if we do that, then the Hasse diagram of the triangulation is the Nu-Tamari lattice. And the length framing is the same, or very similar to the planar framing, except we order the edges by length. So if we again look at vertex 4, this is, by the way, the same graph that we just looked at with the bottom edges here flipped over the horizontal path. So if we look at the incoming edges 1, 2, 3, and the outgoing edges now 1, 2, the incoming edges were ordered the same as they were in the planar framing. The outgoing edges are now in reverse order. And in this case, if we take this framing, the triangulation has its dual graph, the Nu-Tamari lattice introduced by Preville, Vittel, and Viano. However, it's much easier to show that this is the case using a different construction of the Nu-Tamari lattice, which is one given by Ceballos, Padrol, and Sarmiento. And that is using different combinatorial objects known as IJ trees. And the proof is fairly straightforward. You find a correspondence between maximal collections of routes in the graph here to these ij trees, and it's not too hard to do. And yeah, show that the adjacency relations between the simplices is the same as the correlations in the New-Tamari lattice. And something is slightly stronger is true here as well, and is that Ceballos, Padrón, and Sarmiento introduced a new associahedron, which is a polytopic complex that you obtain if you consider also these faces in here, not just the one skeleton. And so the dual of this length frame triangulation of the new Caracal graph is, so of the new Caracal flow polytope is actually the new associahedron. And with that, I have some concluding remarks. I would like to say is that when nu is the classical, in the classical case, when nu is the staircase path, the Hasse diagrams of the Tamari lattice and its corresponding principal order ideal in Young's lattice generated by nu, they've appeared together in certain subdivisions of the Pitman-Stanley polytope, but there they were obtained using different methods, and also they were subdivisions, not triangulations. So in our case now, we have that both of these dual structures can be not only generalized to arbitrary nu, but also they're unified under this umbrella of frame triangulations of this new Caracal flow polytope. And that leads me to a question, something I'm interested in is, are there any other interesting lattice or graph structures on these new Catalan objects obtainable with different framings? Because we can, we pick very natural framings. We pick the planar and the length framing, but you could maybe mix and match those two, or you could pick some other framings, and who knows what kind of graph structures or perhaps lattice structures you might get as well. So that's what I'll end with, and I thank you for your time and welcome any questions from you.
Okay, thank you very much for the talk. Any questions? I don't see questions in the chat. Martin, do you want to unmute yourself and ask the question directly?
Yeah, okay. So my question is, might your technique give you a new proof of the fact that the new Tamari lattice is actually a lattice?
Ooh, good question. Nothing comes to mind, at least immediately. I don't, because we found the dual graph, and then knowing that it is the new Tamari lattice, imposed the lattice structure on there, but there wasn't anything in the method that imposed like a lattice structure on these objects or on the dual graphs themselves. So at least not immediately.
Mm-hmm. Thank you.
I guess I would also like to turn this question around. Does it does the fact that the new Tamari lattice is a lattice give you something interesting on the triangulation? So you have that the collection of simplices now forms a lattice structure.
Perhaps, perhaps it does.
Perhaps it's a solid answer.
Yeah.
Good. Any other questions?
Yeah, I have a question. Have you thought about connections to the Xi arrangement? Because I think if you look at the dominant chamber of the Xi arrangement, its dual graph is also the regions. I mean,
yeah,
could be the interval of Young's lattice you're talking about.
Yeah, that would be an interesting direction to kind of think further. I haven't personally thought about that. I know my advisor Martha Yip has thought about it a little bit, but so that's perhaps an interesting follow-up to consider, but I haven't thought about that now. And I see Alejandro has his hand raised.
It's a quick question. So you mentioned the neosahedron for one of the triangulations.
Yeah.
The other side, what happens when you consider not just the one skeleton, like on the Young's?
Yeah. So then you get this polytuple complex that's as far as I'm aware, it doesn't have a name, but you can do that as well, and you get this polytuple complex with Catalan many vertices, and then a Schroeder combinatorics generalization account for the number of other faces. But I haven't looked into any properties of that particular polytuple complex that you obtain that way, but that could be interesting as well. So thank you.
Okay, so if there are no more questions, then once again, thanks for the talk.